Hello, welcome to this lesson on forces and elasticity. In this particular lesson, we're going to be looking at the required practical for this particular topic, which looks at finding the relationship between the force applied to a material and the extension that force produces on a material. Now, this lesson is suitable for AQA Combined Science, looking at the physics aspect and on the forces unit. Now, in this particular lesson, we'll be looking at describing what Hooke's law is, looking at how to carry out an experiment to prove Hooke's law, identifying on a force extension graph where the inelastic and elastic regions occur, and then finally see if you understand how to calculate the spring constant from a force extension graph. Now, this links into the following part of the AQA Combined Science specification. And in this particular lesson, we're going to focus primarily on discussing required practical activity 18, the relationship between force and the extension for a spring. Now, as mentioned in previous videos, we have looked at the effect of resultant forces in the universe. So a resultant force can cause an acceleration of an object. It can cause energies to change between stores. Now, when energy changes between stores due to a resultant force, we call that work done. But also just be aware that work can also be done when a charge flows. Now, another effect of a resultant force is causing the material to change shape, which we call material deformation. Now, there are three types of material deformation. There's the increase in size due to a force being placed on it, which we call extension. Now, a force which carries out an extension is called either a tensile force or tension. Now, as a result, when the tension is applied, the material gets longer, so we define extension as a positive change. Now, again, for this to take place, as it's a resultant force, more than one force has to be applied to the object. Now, when a deforming force is placed on an object and it decreases in size, that is called compression. And the force which causes compression is called a compressive force. Now, in this particular lesson, we're only going to focus on extension. However, all these cases will also work for compression. So when a compression is applied to a material, it will decrease in size. Now, again, it's going to be a resultant force, so more than one force would have to be applied to the object for this to occur. Now, the third type of deformation is called Bendin. That's when it doesn't change in overall size, but becomes distorted. So it stays the same size, but changes shape. And once again, because we need a resultant force to do this, more than one force has to be applied to the object. Now, there are two ways an object can behave if a resultant force is applied. It can either act elastically or inelastically, and this can occur for either extension, compression, or bending. Now, elastic is when an object regains its original shape after the forces deforming it are removed. So, in all these examples, when the deforming force is removed, the object returns to its original shape. However, an object is inelastic if it doesn't return to its original shape if the forces deforming it are removed. So in these examples, when the deforming force is removed, the object stays deformed, it doesn't return to its original shape. Now, sometimes it's referred to as plastic. Now, I don't like to use this particular term in physics because it can mean something else in chemistry. So when we discuss plastic bottles or plastic bags, that is looking at the chemistry definition of a plastic, a polymer. However, in physics, other objects aside from polymers can act as a plastic. Now, many objects have an elastic region and an inelastic region depending on the deforming force placed upon it. Now, at lower forces, the object acts as elastic, but at higher forces, it acts as an inelastic object. So just to clarify, before we move on, an object is elastic if the object regains its original shape after the deforming force acting on it are removed. An object is inelastic if the object does not return to its original shape if the deforming forces acting on it are removed. Now, many objects are elastic at a certain deforming force, but then inelastic at a larger deforming force. So here, we can measure the effect of the deforming force, whether it be extension, compression, or bending. Okay, however, in this particular example, we're only going to consider extension. Now, extension is measured as the difference in length between the length with the deforming force on the material and the length without the deforming force on the material. So extension is the change in length of material, or delta L. Now, we can then also say it is the length with the deforming force minus the length with no deforming force. So the greater the deforming force, the greater the extension of the object, which would be also true for compression if the force was acting to compress the material. Now, just remember, our extension is measured as the difference in length between the object with the deforming force and without a deforming force. Now, in fact, they're in direct proportion to each other. So when the deforming force doubles, the extension doubles. When the deforming force triples, the extension triples. Now, we call this particular principle Hooke's law. So when this was plotted as a relationship, because it shows direct proportionality, force and extension should show you a straight line through the origin, because a straight line through the origin indicates the two factors of the graph are in direct proportion. Now, if the force extension graph of a material is a straight line through the origin, it's acting in its elastic phase, it's obeying Hooke's law, force and extension are directly proportional. Now, the graph must go through the origin, as when the force is 0, the extension is 0 if you've not measured the length. So that's a common mistake with examination questions. If the actual line of best fit doesn't go through the origin, it tends to be the student has measured the length, not the extension. Now, eventually, over time, when you add more and more and more deforming force onto a material, the material no longer has a directly proportional relationship between deforming force and extension. Now, the point at which this occurs and the line starts to bend is what we call the limit of proportionality. Now, after the limit of proportionality, the material acts as an inelastic. Now, if enough deforming force is eventually placed on it, the object will snap, which is what we call the breaking point. So, to clarify, basically, for any particular material, when you put force against extension, the elastic limit, or the limit of proportionality, is when the line starts to curve. So when the line is curved, the material is acting in the inelastic region, and when the graph is a straight line through the origin, it's acting in its elastic region. Now, it tends to be for all objects, it starts off in its elastic phase, then goes to its inelastic phase, then goes to its breaking point. Now, the gradient of a force extension graph is called the spring constant. Now, this graph, like we mentioned before, places force on the y-axis and the extension on the x-axis. Now, as a force can cause an extension, this means the line should go through the origin. Now, if it doesn't go through the origin, like we mentioned before, the experimenter has probably measured the length, not the extension. Now, the spring constant is the amount of force needed to extend the material by 1 meter. It's how stiff an object is. So the stiffer the object, the larger the spring constant, the stiffer the object, the more difficult it is to extend. Now, the spring constant can only be taken in the straight line section of the graph. That's because the gradient has to be a constant, because the spring constant, as the name suggests, is actually a constant. Now, to take the gradient, remember you draw a right angle triangle on the graph with the line of best fit providing the hypotenuse. Now, you try to make your gradient triangle as large as possible, because this will increase the validity of your results as you're considering more values for your gradient. So what you would do is you'd have your change in y values and your change in x values. Now, the gradient is the change in y divided by the change in x. So it's the change in force over the change in extension, which is force over extension. So the gradient is our spring constant. Now, this allows us to work out our units of the spring constant, which are newtons per meter, because the units of the y-axis are in newtons and of the x-axis are in meters. So that allows us to the spring constant to have a units of newtons per meter. So we can clarify and define the spring constant as the proportionality constant between the deforming force and the extension that it causes. So it means that for a material that obeys Hooke's law, deforming force equals spring constant times by extension. But this is only true for elastic objects and not inelastic ones. Now, when this happens, This deforming force causes work to be done on the material. So the energy will be stored in the material as an elastic potential energy store. Now you know the equation to work out an elastic potential energy store from physics paper 1, which is elastic potential energy is equal to a half times by spring constant times by the extension of the material squared. Now, this deforming force equals spring constant times by extension is an equation you need to memorize for your examinations. Now, if the material is obeying Hooke's law and force and extension are in direct proportion, the line will be a straight line through the origin. As a result, we can observe that when it's a straight line through the origin, you can measure the spring constant, the object is acting elastically, it's obeying Hooke's law. But once you go past that particular limit of proportionality, the line will start to curve. You can't take the spring constant from that particular section because the material no longer obeys Hooke's law, and so as a result is acting as an inelastic. So when an object obeys Hooke's law, it's an elastic energy store. When it doesn't obey Hooke's law, it's inelastic. Now, as we mentioned before, if it's obeying Hooke's law, force and extension in direct proportion, it's a straight line through the origin. Now, the limit of proportionality is where the line starts to curve, when it starts to act as an inelastic. So it's no longer showing direct proportionality because it's not a straight line through the origin. And then eventually, once you have a certain amount of deforming force, the material will reach breaking point. Now, once the material passes that limit of proportionality, before it hits the breaking point, it will be acting as an inelastic. Now, in your required practical, you need to be able to find experimentally the relationship between the deforming force and the extension of an elastic object, which in this example is a spring. So what you'll need for this particular practical is a clamp stand, a clamp, a ruler, a boss, a spring, a G-clamp or a counterweight, a pointer, which will probably be a ruler, and then 10 1 Newton weights. So you'll set up the apparatus as seen on this particular diagram. You'll then take an initial reading when the spring is only suspended for the clamp, which is your reading for 0 newtons. That's the original length of the spring. A mass hanger is then placed on the spring. The length of the spring is recorded and the extension of the spring is then calculated, with the stretch length minus the original length being the extension. You then remove the mass hanger from the spring so it recoils to its original length. You then repeat the previous step with a 1 Newton weight, and you keep going in 1 Newton weight intervals from 1 to 2 to 3 to 4 to 5 to 6 to 7 to 8 to 9 to 10. Each time you'll measure the length of the spring when there's no weight placed on the spring, and obviously if it's elastic still it should be the same value each time. You'll measure the stretch length and derive the extension. So as a step-by-step guide, the first thing you'll do is you'll get a clamp stand. You then attach a boss and a clamp to your clamp stand. You'll then place a counterweight on the clamp stand to stop the stand from toppling over. What you'll then do is you'll place the clamp stand over the edge of the table because that'll allow your spring to fully extend without hitting the table, as shown here. You'll then place a meter ruler vertically in the clamp. Now it's very, very, very important your ruler is placed parallel because this reduces something in physics called parallax error when you're reading the length of the spring. So you may wish to use a set square to ensure your ruler is vertical. Basically, a parallax error is an error occurring when you are not either dead on or the measuring device is not set up completely dead on with the equipment, and as a result there's a variance in the measurement. Now you place the top of the ruler in the clamp, which will give you most of the ruler to take measurements with. Now you'll get a spring, and you need to use the same spring throughout the investigation, and it should be an elastic material. Now don't deform the spring with your hands before you use it. I know it's tempting to have a play with the spring beforehand, but that can actually affect its elastic properties. What you then do is you set up the spring, ruler and clamp as so. You should then measure the original length of the spring, measure from the top of the coil to the bottom of the coil of the spring. Now technically it doesn't make a difference where you measure the length of the spring from, as long as you're keeping it constant throughout the investigation. However, the top coil and the bottom coil of the spring are the most distinguishable parts of the spring, so the easiest to measure. Now, it's best practice to use a pointer to help you identify the top and the bottom parts of the spring against the measuring ruler. Now, we call this idea of a marker or a pointer the fiducial marker. Now, it's best practice to use this on both the bottom and the top of the spring to work out what those values are, to work out your length of your spring. Now, you'll then retrieve 10 1 Newton weights, which will be used to apply the deforming force on the spring. Now, remember, the holder itself has a weight of 1 Newton. So as a result, that particular mass hanger has a weight of 1 Newton. You place this weight on the spring, and that will provide a tensile force causing extension. Now, you will measure the extended length now by the same principle, and you can work out the extension caused by the deforming force by doing the extended length minus the original length. Now, again, please use the same practice as you did previously to measure the stretched length. So use a fiducial marker or a pointer to find the values on the ruler for the top coil and the bottom coil. Now, the use of a fiducial marker reduces this parallax error in the investigation and makes the result more accurate. Now, you'll then remove the 1 Newton force and measure the original length of the spring. Now, this is the next reading measurement. Now, as the object's elastic, it should be the same result as previously, but you've always got to check to ensure that's the case. Now, again, you'll then measure the original length of the use of a pointer or a fiducial marker on the top and the bottom coils. You'll then repeat the process again because it's making the experimental values more accurate, but this time you're going to use a 2 Newton weight. You'll then place the 2 Newton weight on the spring. That will cause the spring to extend, and then you can measure the extended length and work out your extension by doing extended length minus original length, and you can take each value for 2, 3, 4, 5, 6, 7, 8, 9, 10 newtons. Now, always ensure when you're doing this practical, you're always parallel to the ruler when you're taking your measurements. Try to refrain from using your own ruler, as that can tilt easily. Use the ruler that's been clamped vertically, and also always ensure the spring is not oscillating when measurements are being taken. Now, as we said before, always try and use a fiducial marker as a pointer to ensure it reduces that parallax error, as mentioned previously. Now, with your observations, you should fill in the following result table with your original length, which is without any deforming force on there, your stretched length, which is the length with the weight acting as producing the deforming force on the object, then the extension, which is the stretched length minus the original length. Now, you would then draw a graph, okay, where you put the force on the y-axis and the extension on the x-axis. In theory, if you do this experiment accurately, you should draw a line that best fit in, which is a straight line through the origin, because the limit of proportionality for your material is when the line that best fit starts to curve, and the gradient of the straight line section of the graph is the spring constant. Now again, when working this out, draw your gradient triangle as large as possible, as it increases your validity of results as you're considering more data in your value. Now, these are my sample results when I did the experiment myself. Now, a few things when looking at this particular data. Number one, as you look through this, all values in each column are given to the same number of decimal places. Now, all headings are given with units. And finally, as well, really importantly, the number of decimal places is decided by the number of decimal places the measuring device can record to. So the length was recorded to 3 decimal places because the ruler we used could measure to 3 decimal places. Now, you should always have the number of decimal places in a value be the same as the number of decimal places a device can record to. That's extremely important. Now, here is the results for my experiment drawn on a graph. Now again, a few things. Firstly, in my results, the spring didn't reach the limit of proportionality as there's no curve. It's a straight line through the origin. Now again, for the best practice for a graph, you label your axes with headings and units, your points are plotted correctly, you've got your points plotted on an appropriate scale, a line of best fit drawn, which in theory should be a straight line through the origin, and then to determine your spring constant, you should draw a gradient triangle as large as possible because you're considering the most results, so it increases the validity. You then do your change in y divided by your change in x, and that will work out your gradient of your spring constant. And this example, it was 27 newtons per meter. Now that's important because you should always give gradient values to the correct no significant figures with the correct units. So in my investigation, my spring had a spring constant of 27 newtons per meter, which means that that spring needs 27 newtons of tensile force to extend it by 1 meter. So in this lesson, you should be able to describe what Hooke's law is, understand what the experiment is to prove Hooke's law, identify on a force extension graph where the inelastic and elastic regions occur, and finally how to calculate the spring constant from a force extension graph. Thank you very much for listening to this lesson and have a lovely day.